Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Gravity is the invisible architect of the universe, an unseen force that dictates the motion of planets, moons, and stars. In our own solar system, gravity is the silent hand that sculpts celestial landscapes, orchestrates planetary orbits, and preserves cosmic harmony. From the blazing sun at the center to the icy comets on the outskirts, every celestial body is bound by gravity, pulled into a cosmic dance that has lasted for billions of years. Without gravity, there would be no planets circling stars, no moons embracing their planets, and certainly no life on Earth as we know it. It is gravity that knits together the solar system into a coherent structure, guiding the paths of planets and smaller objects in predictable ways, while occasionally stirring cosmic chaos. At the heart of the solar system lies the Sun, a colossal sphere of hot plasma whose gravitational pull dominates everything in its vicinity. The Sun contains more than 99% of the total mass of the solar system, making it the ultimate anchor around which all planets revolve. Its gravity is the invisible tether that keeps Earth and its neighboring planets from drifting into the void of space. Each planet follows an elliptical orbit dictated by a delicate balance between gravitational pull and the planet's own inertia. If the Sun's gravity were slightly stronger, planets would spiral inward, drawn closer until they collided with the fiery surface. If it were slightly weaker, planets would drift away, abandoning their orbital paths to wander as cosmic vagabonds. Gravity thus maintains the equilibrium of the solar system, ensuring that celestial bodies remain in their respective zones for billions of years. The formation of the solar system itself is a story written by gravity. Around 4.6 billion years ago, a vast cloud of gas and dust known as a solar nebula began to collapse under its own gravitational pull. As the particles drew closer together, the center of the cloud grew hotter and denser, eventually igniting nuclear fusion and giving birth to the Sun. Meanwhile, the remaining material flattened into a rotating disk where gravity continued its work. Dust particles clumped together to form planetesimals, small rocky bodies that gradually merged into larger protoplanets. Gravity acted as both the glue and the sculptor, attracting material and carving out the distinctive structure of the solar system. It determined not only which objects grew into planets, but also where they formed, with heavier elements condensing closer to the Sun and lighter gases forming the giant planets farther away. Beyond the planets, gravity governs the intricate ballet of moons, asteroids, and comets. Moons, for example, are often captured by the gravitational pull of their parent planets. Some, like Earth's moon, may have formed from the debris of colossal collisions, while others, like Neptune's moon Triton, are likely captured objects from distant regions of the solar system. Gravity shapes their orbits, sometimes locking them into resonances where their orbital periods maintain simple ratios with each other. These gravitational relationships create stability, preventing moons from colliding or being flung into space, and in some cases driving tidal forces that reshape planetary surfaces over eons. Even the asteroid belt and the distant Kuiper belt are products of gravitational interactions. The asteroid belt between Mars and Jupiter represents material that never coalesced into a planet, in large part due to Jupiter's immense gravity. The giant planet's gravitational influence stirred the region, preventing the accumulation of material and scattering smaller bodies into elongated orbits. Similarly, the Kuiper belt and the more distant Oort cloud are shaped by the combined gravitational effects of the Sun and passing stars, as well as occasional perturbations from giant planets. These regions serve as repositories of primordial material, frozen remnants from the solar system's formation, their positions and trajectories dictated by gravitational forces over billions of years. Gravity's influence extends to the dynamics of planetary motion and rotation. Planets are not just passive travelers around the Sun. Their own gravity affects their shape and internal structure. The interplay between centrifugal forces from rotation and gravitational pull gives planets their characteristic oblate shapes. Gas giants like Jupiter and Saturn are noticeably flattened at the poles due to rapid rotation, while smaller rocky planets maintain near-spherical forms. Gravity also drives geological activity. It creates pressure that shapes planetary cores, fuels volcanic activity, and even contributes to magnetic field generation in planets like Earth and Jupiter. Tidal forces, a manifestation of gravity, stretch and compress planets and moons, generating heat and occasionally triggering volcanic eruptions, as seen spectacularly on Jupiter's moon Io. Even the apparent stability of the solar system is a delicate product of gravitational interactions. Planets tug on each other, sometimes subtly altering orbits over millions of years. These perturbations can lead to orbital resonances, where two bodies exert regular periodic gravitational influence on each other, resulting in stable or chaotic configurations. The resonance between Neptune and Pluto, for instance, ensures that despite Pluto crossing Neptune's orbit, the two bodies never collide. Such gravitational choreography demonstrates that the solar system is not a rigid structure, but a dynamic, ever-evolving network of forces, balanced delicately over cosmic time. Comets and meteoroids, too, are guided by gravity on their long journeys. Comets originating from the distant Oort cloud can remain in near-invisible orbits for millennia, only to be nudged by the gravitational influence of passing stars or galactic tides, sending them hurtling toward the sun. As they approach, the sun's gravity bends their paths into elongated trajectories, while heat from the sun vaporizes their ices, creating the iconic glowing tails. Meteoroids, whether born from collisions or remnants of comets, also follow paths determined by gravitational forces, occasionally entering Earth's atmosphere and burning up in brilliant streaks, revealing the constant gravitational interplay within our solar neighborhood. The role of gravity in shaping the solar system is not static, but continuous. It determines not only where planets and smaller bodies are today, but also their potential future trajectories. Over immense timescales, gravitational interactions can lead to dramatic changes. Planets can migrate, moons can be captured or lost, and objects can be ejected entirely from the solar system. The very structure of the solar system, with inner rocky planets, outer gas giants, and distant icy bodies, is a reflection of billions of years of gravitational negotiation. It is a story of balance, tension, and subtle negotiation between celestial bodies, where gravity is both a gentle guide and a relentless force. Even our own planet owes its stability to gravity. Earth's gravitational relationship with the moon creates tides, moderates rotation, and stabilizes the axial tilt, which in turn regulates climate and seasons. Without gravity's regulating influence, Earth's spin could wobble wildly, destabilizing the environment and challenging the emergence of life. Similarly, Jupiter's immense gravity acts as a cosmic shield, deflecting or capturing many potential impactors that might otherwise threaten inner planets. The solar system, therefore, is a system of interdependent gravitational relationships, each body influencing the others in an intricate web of attraction. Gravity's reach extends beyond individual bodies to the solar system as a whole, influencing how it moves through the galaxy. The Sun, along with its retinue of planets, moons, and minor objects, orbits the center of the Milky Way galaxy, held in place by the combined gravitational pull of the galaxy's stars, gas, and dark matter. The solar system's path is not a simple circle, but a complex motion that oscillates above and below the galactic plane, shaped by the gravitational landscape of the Milky Way. This movement introduces additional dynamism, as interactions with passing stars or molecular clouds can subtly influence the orbits of distant Oort cloud objects, sometimes sending them plunging inward as comets. Gravity also plays a critical role in cosmic collisions and the evolution of planetary systems. When protoplanets collided in the early solar system, gravity determined how much material coalesced into planets versus how much was scattered. These collisions were not chaotic accidents, but guided by gravitational forces that determine the likelihood, angle, and outcome of each encounter. Even today, near-Earth objects can experience gravitational slingshots during close approaches to planets, changing their velocities and orbits in in ways that echo the early formation of the solar system. The solar system, therefore, is not merely a static structure, but a living, breathing system continually molded by gravity. In addition to shaping motion and structure, gravity also influences the internal composition and evolution of celestial bodies. Massive planets compress their interiors under their own gravity, generating heat that drives internal convection and contributes to the creation of magnetic fields. Stars, like the Sun, are powered by the balance between gravity and nuclear fusion, with gravity compressing core material to the extreme densities required for fusion to occur. Without gravity, not only would planets fail to form, but stars themselves could not ignite, leaving the universe cold and dark. Gravity is thus the invisible architect that builds and sustains the very energy sources that illuminate the solar system. The study of gravity also helps us predict the future evolution of the solar system. By understanding gravitational interactions, scientists can model planetary motions millions or even billions of years into the future. These models reveal that while the solar system is remarkably stable, it is not immune to change. Planets may slowly migrate, orbits may shift, and gravitational nudges from passing stars or molecular clouds may perturb distant objects. Long-term studies of gravitational effects allow us to anticipate potential impacts or orbital instabilities, revealing the profound influence of this unseen force across both space and time. As we observe distant exoplanetary systems, the importance of gravity in shaping planetary architectures becomes even clearer. Systems with hot Jupiters, tightly packed planets, or eccentric orbits illustrate how variations in gravitational dynamics can lead to dramatically different planetary arrangements. By comparing these systems with our own, scientists gain insight into how gravity sculpts the possibilities of planetary formation and evolution, reaffirming the universal role of this fundamental force. Gravity's influence is also evident in phenomena like planetary rings and Trojan asteroids. Saturn's rings, composed of countless particles ranging from dust grains to boulders, are maintained by a delicate balance of gravitational forces. Moons shepherd the rings, while gravity prevents the particles from dispersing into space. Similarly, Trojan asteroids, which share Jupiter's orbit, occupy stable regions called Lagrange points, where the gravitational pulls of the Sun and Jupiter balance perfectly. These examples underscore gravity's ability to maintain complex structures over vast distances and timescales, revealing the sophistication of celestial mechanics. Throughout the solar system, gravity operates at multiple scales, from the minute interactions between particles in a protoplanetary disk to the majestic orbits of planets around the Sun. It is the force that enables the formation of stars, planets, moons, comets, and asteroids, and dictates their behavior over billions of years. Every orbit, every tidal pull, every cosmic collision is a manifestation of gravity's omnipresent hand. Even as human understanding expands, the fundamental influence of gravity remains a cornerstone of astrophysics, shaping not only our solar system, but the universe at large. Gravity also plays a role in the cycles of destruction and creation within the solar system. Collisions between asteroids and comets, guided by gravitational encounters, can create debris that eventually coalesces into new objects. Impacts on planets and moons can carve craters, release material, and alter surfaces through the governance of gravitational dynamics. These processes illustrate how gravity not only preserves order, but also drives change, continually reshaping the solar system in subtle and dramatic ways. The interplay of attraction and motion ensures that the solar system remains a dynamic and evolving environment, rather than a static celestial arrangement. And even when, as humanity ventures beyond Earth, gravity continues to guide exploration. Space missions rely on gravitational assists to travel efficiently across the solar system, using the pull of planets to accelerate spacecraft and adjust trajectories. Observations of gravitational effects, from planetary motions to orbital perturbations, have led to discoveries of new planets, moons, and distant objects, showcasing how understanding gravity allows us to map and navigate the cosmos. From the first telescopic observations to modern space probes, our knowledge of gravity has been instrumental in expanding our reach and comprehension of the solar system. In essence, gravity is both the sculptor and the stage upon which the solar system's drama unfolds. It shapes the formation, structure, and motion of every celestial body, maintaining balance while enabling dynamic change. From the fiery core of the sun to the icy outskirts of the Oort cloud, gravity governs the past, present, and future of the solar system. Its influence permeates every orbit, every collision, and every tidal wave, quietly orchestrating the cosmic ballet that has continued for billions of years and will persist for eons to come. Understanding gravity is not merely an academic exercise. It is the key to comprehending our place in the cosmos and appreciating the intricate forces that make our solar system a coherent, thriving, and dynamic system. The story of gravity in the solar system is far from over. As we continue to study planetary formation, orbital dynamics, and interstellar interactions, we uncover new layers of complexity, revealing that gravity's role is as subtle as it is profound. It teaches us that even in the vast emptiness of space, invisible forces govern structure, order, and motion, and that our solar system, for all its apparent stability, is a product of a delicate balance maintained by the universal force of attraction. By exploring and understanding gravity, we unlock the secrets of the solar system's past and gain insights into its future, reminding us that in the cosmic dance of planets, moons, and stars, gravity is the ultimate choreographer. Gravity does not act in isolation. It creates patterns and resonances that define the stability of the solar system. The planets, from Mercury to Neptune, move along elliptical paths that are subtly perturbed by the gravitational influence of neighboring planets. These perturbations can lead to phenomena known as orbital resonances, where the orbital periods of two celestial bodies maintain a simple ratio. For instance, Jupiter's moons Io, Europa, and Ganymede are locked in a 1:2:4 resonance. This gravitational locking ensures their orbits remain stable, while also generating tidal heating within the moons, driving volcanic activity on Io, and possibly sustaining subsurface oceans on Europa. Orbital resonances are a testament to how gravity shapes not only motion, but also internal characteristics of celestial bodies. The immense gravity of the gas giants also plays a protective role. Jupiter, with its massive gravitational field, acts as a cosmic shield for the inner solar system. It captures or deflects many comets and asteroids that might otherwise collide with Earth or Mars. These interactions are not violent coincidences, but predictable outcomes of gravitational dynamics. The solar system, therefore, can be seen as a finely tuned machine where giant planets stabilize the environment for smaller, rocky worlds to develop complex surfaces and potentially life. Without the presence of such gravitational giants, the inner solar system could be a far more chaotic and hostile place. Gravity also sculpts the delicate structures we see around planets. Saturn's rings are composed of countless ice and rock particles, each orbiting under the influence of Saturn's gravity. Moons, called shepherd satellites, maintain the sharp edges of the rings, their gravity nudging particles into dense bands or gaps. In the asteroid belt, Jupiter's pull prevents the accumulation of a planet, scattering objects into elliptical orbits and producing regions of stability called Kirkwood gaps. These gaps reflect the resonant gravitational interactions between Jupiter and asteroids, illustrating how even seemingly empty space is organized by invisible forces. Even in the outer solar system, gravity dictates the behavior of distant icy bodies. The Kuiper Belt, home to Pluto, Eris, and countless smaller objects, lies just beyond Neptune. Objects in this region are in constant gravitational dialogue with Neptune, with some caught in resonances that protect them from collisions. Farther still, the Oort cloud stretches nearly a light year from the Sun, its cometary resonance delicately balanced by the Sun's gravity and perturbed by passing stars and galactic tides. Occasionally, these disturbances send comets on long voyages toward the inner solar system, demonstrating how gravity connects the farthest reaches of the Sun's influence to the planets that circle it. The dynamics of gravity also shape the evolution of moons and planetary surfaces. Tidal forces, a direct consequence of gravitational attraction, create friction within planetary interiors. On Earth, the moon's gravity generates ocean tides, slowly altering the planet's rotation rate over billions of years. On Jupiter's moon Io, tidal stretching generates tremendous heat, fueling active volcanoes. Even Pluto and its moon Charon exert tidal forces on each other, locking their rotations in a gravitational embrace that shows how closely gravity ties the destiny of worlds together. Gravity is not a static force. It operates over immense scales and time frames, producing gradual but profound effects. Over millions of years, the gravitational pull of one planet on another can shift orbits slightly, potentially leading to dramatic consequences. Numerical simulations suggest that, given enough time, interactions between planets can cause orbital instabilities or even ejections from the solar system. Yet the solar system has remained remarkably stable for over 4 billion years, a testament to the intricate gravitational choreography that maintains balance even in the face of potential chaos. Even human exploration of space relies on gravitational principles. Spacecraft routinely use gravitational assists, or slingshots, to gain speed and alter trajectory without expending extra fuel. By carefully approaching a planet at a precise angle, a spacecraft can absorb a fraction of the planet's orbital momentum, sending it toward distant destinations. Missions such as Voyager, Cassini, and New Horizons exemplify how humanity harnesses gravity to explore the solar system, demonstrating that understanding these forces is essential not only for theoretical astrophysics, but for practical navigation among the stars. The history of planetary formation itself cannot be separated from gravity. Protoplanetary disks, composed of gas and dust around young stars, rely on gravitational attraction to clump particles into larger aggregates. Over time, these planetesimals collide and merge, growing into planets. In the inner regions of a system, where temperatures are high, only rocky and metallic materials survive, forming terrestrial planets. Farther out, cooler conditions allow gases to condense, forming massive gas giants. Gravity determines which materials remain in which zones, ultimately shaping the architecture of the planetary system. Comets provide a vivid example of gravity's ongoing influence. Long-period comets from the Oort cloud can take millions of years to orbit the Sun, their paths shaped by tiny gravitational nudges over time. As they approach the inner solar system, the Sun's gravity bends their trajectories into elongated orbits, sometimes leading them dangerously close to planets. Short-period comets, originating from the Kuiper Belt, are trapped in more predictable orbits, often interacting with the giant planets, which further sculpt their paths. Every tail that stretches across the night sky is a visible trace of gravitational forces in action, a reminder that the solar system is alive with invisible currents of attraction. Gravity's influence also extends to minor bodies like asteroids and dwarf planets. Ceres, the largest object in the asteroid belt, maintains a spherical shape due to its self-gravity, while smaller asteroids remain irregular because gravity is insufficient to overcome material strength. Pluto and Eris, on the other hand, are fully rounded, demonstrating how mass and gravity determine not only motion, but form. Even the surface features of these bodies, craters, mountains, and icy plains, reflect a balance between gravitational collapse and material resistance, revealing the subtle yet powerful role of attraction in shaping worlds. Beyond our solar system, the study of gravity helps explain planetary systems around other stars. Exoplanets with tightly packed orbits, eccentric paths, or unusual resonances all demonstrate how gravity dictates the possibilities of planetary architecture. By comparing these systems with our own, astronomers gain insight into how gravity shapes planetary migration, stability, and potential habitability. The patterns observed remind us that gravity is a universal force, acting consistently across billions of stars, crafting planetary systems in predictable yet astonishingly diverse ways. Even in the most extreme cases, gravity defines outcomes. Collisions between large planets in the early solar system were guided by gravitational dynamics that determined whether material merged, fragmented, or scattered. The moon's formation, thought to result from a giant impact with Earth, illustrates how gravitational interactions can produce entirely new worlds. Similarly, the tilt of Uranus, possibly caused by a massive collision, reflects gravity's role in determining planetary rotation and orientation. These dramatic events, though rare, highlight the profound influence of gravity not only in shaping orbits, but in sculpting planetary history itself. The outer solar system, with its distant planets and icy bodies, further illustrates gravity's reach. Neptune, despite its distance, exerts a measurable influence on Kuiper belt objects, locking some into resonances and scattering others into elongated orbits. Occasionally, perturbations from passing stars or molecular clouds alter the trajectories of Oort cloud comets, sending them plunging toward the inner solar system. Gravity, therefore, connects the furthest reaches of the Sun's domain to the planets we observe, maintaining coherence across vast expanses of space. Even in the context of time, gravity's effects accumulate, shaping the solar system over billions of years. Planetary migrations, resonances, tidal evolution, and orbital perturbations all unfold over immense timescales, producing subtle but permanent changes. Mercury's eccentric orbit, Venus's slow rotation, and the distant orbits of trans-Neptunian objects are all legacies of long-term gravitational interactions. Each feature of the solar system is a fingerprint of gravity's enduring influence, a record of the invisible force that governs motion, formation, and evolution. Gravity also orchestrates cycles of destruction and renewal. Collisions, tidal disruptions, and orbital shifts all result from gravitational forces, creating debris that may coalesce into new objects or impact existing worlds. Meteor showers, for instance, occur when Earth passes through streams of debris left by comets, tracing gravitationally guided paths through space. Craters on planets and moons preserve the history of these interactions, providing a visible record of how gravity shapes not only motion, but the surfaces and environments of celestial bodies. In human terms, understanding gravity has revolutionized our ability to explore and predict the solar system. Mathematical models of gravitational dynamics allow us to predict planetary positions, chart spacecraft trajectories, and anticipate potential collisions. Observations of perturbations in known orbits even lead to the discovery of previously unknown objects, as was the case with Neptune's discovery based on Uranus's gravitational anomalies. Gravity is not merely a natural force, it is a tool through which we interpret, navigate, and interact with the cosmos. The interplay of gravity and motion produces phenomena that are at once predictable and astonishing. Eclipses, tidal locking, orbital resonances, and cometary tails all manifest from the simple principle of attraction. Yet the resulting behaviors are often complex, creating patterns and structures that continue to inspire wonder. The solar system is a living laboratory, demonstrating how gravity sculpts order from chaos, balances motion with force, and enables the emergence of complex systems from simple physical laws. Gravity's influence is evident in the fine details of each planet's motion and environment. Mercury, the innermost planet, experiences extreme variations in temperature, partly due to its elliptical orbit shaped by the gravitational tug of the Sun and the slight perturbations from Venus and Jupiter. Its rotation is locked in a 3-to-2 resonance with its orbit, completing 3 rotations for every 2 revolutions around the Sun, a gravitational arrangement that stabilizes its spin while creating dramatic day-night cycles. Venus, with its slow retrograde rotation, exhibits a complex interaction of solar gravitational forces and possible past collisions, suggesting that gravity combined with cosmic events can yield unexpected rotational dynamics. Earth, our home planet, demonstrates gravity's profound role in sustaining life. The gravitational pull of the moon generates ocean tides, which regulate climate and facilitate nutrient circulation in the seas. This tidal interaction also slows Earth's rotation gradually, lengthening the day over millions of years. Additionally, gravity maintains the axial tilt of 23.5 degrees, creating the seasonal variations critical for diverse ecosystems. Mars, slightly smaller than Earth, shows evidence of past water flows and seasonal changes in polar ice caps, both influenced by the planet's own gravity and interactions with the Sun and Jupiter. Gravity shapes the atmosphere, surface pressure, and potential habitability of planets, revealing how fundamental this force is to planetary character. The gas giants, Jupiter and Saturn, dominate the solar system through their immense gravitational influence. Jupiter's mass is more than twice that of all other planets combined, and its gravity shapes not only its moons, but also the asteroid belt, ensuring that many objects never coalesce into a planet. The Trojan asteroids, sharing Jupiter's orbit, are held in place by precise gravitational balance at Lagrange points, regions where the pull of the Sun and Jupiter cancel out, creating stable zones. Saturn, with its elaborate ring system, demonstrates gravity's capacity to sculpt intricate structures, where moonlets shepherd ring particles, maintaining clear divisions and preventing dispersion. These examples illustrate how massive planets exert gravitational control over regions extending millions of kilometers. Uranus and Neptune, the ice giants, showcase gravity's subtle yet powerful effects at the outer reaches of the solar system. Uranus's extreme axial tilt, likely the result of a massive collision, leads to unique seasonal variations, while Neptune's gravitational interactions influence the orbits of distant Kuiper Belt objects. Triton, Neptune's largest moon, is believed to be a captured Kuiper Belt object, whose retrograde orbit highlights gravity's role in capturing and stabilizing distant celestial bodies. The delicate gravitational interplay at these distances demonstrates that even weak forces over vast scales can produce lasting stability or dramatic orbital changes. Dwarf planets, asteroids, and comets further reveal the role of gravity across different scales. Pluto, Eris, Haumea, and Makemake, despite their smaller masses, exhibit nearly spherical shapes, showing that self-gravity molds their structure over time. Asteroids, depending on size and composition, range from irregular shapes to nearly rounded forms, as in the case of Ceres. Comets, originating from the Kuiper Belt or Oort cloud, have their elongated orbits and spectacular tails guided by the sun's gravity. Sometimes perturbed by passing stars, galactic tides, or planetary encounters. These minor bodies serve as reminders that gravity governs both motion and form, from the largest gas giants to the smallest icy wanderers. Beyond individual objects, gravity shapes the solar system as a dynamic network. Planetary migrations, occurring in the first hundreds of millions of years, redistributed mass and sculpted current orbits. Jupiter and Saturn likely underwent migration, their gravitational influence altering the orbits of proto-Earth, Mars, and asteroids, shaping the architecture of the inner solar system. Such migrations explain why Mars is smaller than Earth and Venus, and why the asteroid belt remains a collection of scattered remnants rather than a planet. These processes, all driven by gravity, reveal that the solar system is not a static arrangement, but an evolving system, continually sculpted by attraction over eons. The Oort cloud, a distant spherical shell of icy bodies, is an extreme example of gravity's reach. Extending nearly a light year from the sun, it is bound only weakly by solar gravity, making it sensitive to the gravitational influence of passing stars or molecular clouds. Occasionally, these perturbations send long-period comets plunging toward the inner solar system, connecting the farthest reaches of the sun's domain with the planets we see. Such interactions demonstrate gravity's power to orchestrate events across vast distances and timescales, linking distant, frozen remnants to the dynamic inner solar system. Tidal forces arising from gravity are central to the evolution of planetary and lunar environments. On Earth, the moon's gravity generates ocean tides, but on moons like Io, tidal flexing creates intense volcanic activity. Europa, under Jupiter's gravitational pull, may harbor a subsurface ocean kept liquid by tidal heating, raising possibilities for extraterrestrial life. Gravity thus not only directs motion, but also drives internal processes, shaping geologic activity, magnetic fields, and even the potential for life across the solar system. It is a force that operates both externally, in orbital mechanics, and internally, influencing planetary evolution. Space exploration has leveraged gravity in innovative ways. Gravitational assists allow spacecraft to reach distant planets efficiently, gaining speed from planetary motion without additional fuel expenditure. Missions such as Voyager, Cassini, and New Horizons relied on precise gravitational calculations to navigate the solar system, demonstrating humanity's ability to harness this fundamental force. Observations of orbital perturbations have even led to the discovery of new planets, as in the case of Neptune, whose existence was predicted from the gravitational influence on Uranus. Gravity is thus both a natural sculptor and a tool for human exploration, bridging understanding and application. Gravity also preserves order amidst potential chaos. Planetary collisions, rare but transformative, are shaped by gravitational dynamics. The Moon's formation, resulting from a collision between Earth and a Mars-sized body, created a new satellite whose orbit continues to evolve under Earth's gravity. The tilt of Uranus and the eccentric orbit of Mercury illustrate how gravity governs rotational and orbital characteristics, sometimes producing surprising configurations. Over billions of years, these interactions accumulate, creating the diverse range of planetary behaviors observed today. In minor bodies, gravity determines structure and evolution. Ceres' spherical form contrasts with irregularly shaped smaller asteroids, illustrating the threshold where gravity overcomes material strength. Comets, often described as dirty snowballs, experience sublimation as they approach the sun, producing tails whose shape is influenced by the interplay of solar radiation and gravitational forces. Even dust particles within rings and debris disks are guided by gravity, maintaining ordered structures in otherwise chaotic regions. Across scales from particles to planets, gravity is the organizing principle of the solar system. The interplay of gravitational forces also influences planetary atmospheres and potential habitability. Earth's gravity retains a breathable atmosphere, while Mars's weaker pull allows gases to escape over time. Venus's dense atmosphere is partly a result of its mass and gravity, trapping heat and creating a runaway greenhouse effect. Gravity interacts with other forces: solar radiation, planetary rotation, magnetic fields, to shape climates, surface conditions, and the potential for life. This demonstrates that gravity is not an isolated phenomenon, but interacts dynamically with other physical processes. As we look toward the future of the solar system, gravity continues to play a decisive role in shaping its evolution. Over billions of years, planets may slowly shift in their orbits due to subtle gravitational interactions with neighboring planets and small bodies. These interactions, though often imperceptible on human timescales, accumulate to produce measurable changes. Mercury's orbit may become slightly more eccentric, and the orbits of outer planets may gradually evolve under the combined gravitational influences of each other and passing stars. Even distant dwarf planets in the Kuiper Belt may experience altered trajectories, sometimes leading them to cross paths with other bodies or venture inward as comets. Gravity, though invisible, remains the ultimate arbiter of cosmic destiny, orchestrating both stability and change. The solar system does not exist in isolation. Passing stars, molecular clouds, and the gravitational field of the Milky Way itself exert subtle influences on the outermost regions. Objects in the Oort cloud, loosely bound by the sun's gravity, are especially vulnerable to these forces. Occasionally, a passing star can perturb comets, sending them into the inner solar system, where they may become spectacular visitors or even pose potential hazards to planets. Galactic tides, the gravitational influence of the Milky Way's mass, also shape the distant boundaries of our system. Gravity ensures that the solar system is not merely a collection of bodies around the sun, but a system intimately connected to the galaxy itself, sensitive to both internal and external forces. Even within the inner solar system, gravity maintains a delicate balance. The giant planets act as guardians, preventing an excess of asteroids and comets from impacting the terrestrial planets. Jupiter's gravity in particular deflects or captures many potentially dangerous objects, shielding Earth and allowing life to thrive. This protective role highlights the interconnectedness of the solar system. Each planet's gravity contributes to a complex network that regulates motion, collisions, and stability. Without such gravitational relationships, the inner planets might experience far more frequent and destructive impacts, potentially altering the course of life and planetary development. Gravity also guides the potential futures of moons and satellites. Tidal interactions slowly alter rotational periods, orbital distances, and internal heating. Earth's moon is gradually receding, lengthening days on Earth, while tidal friction continues to generate volcanic activity on moons like Io. Even distant icy moons in the outer solar system, such as Europa and Enceladus, maintain subsurface oceans due to gravitational heating, suggesting that gravity may play a role in preserving conditions suitable for life far from the sun. These ongoing effects demonstrate that gravity is not merely a historical force, but an active agent in the continuous evolution of celestial bodies. As humanity advances into space exploration, understanding gravity is essential. Gravitational physics informs spacecraft navigation, mission planning, and hazard prediction. Gravitational assists allow probes to reach distant planets efficiently, while models of orbital dynamics predict the long-term evolution of potentially hazardous objects. Observations of gravitational perturbations have even led to discoveries of unseen bodies, reinforcing that gravity is both a fundamental natural law and a practical tool for exploration. Studying gravity helps humanity understand not only our cosmic neighborhood, but also the principles governing planetary systems across the galaxy. The role of gravity in shaping the solar system also extends to the formation and evolution of planetary systems around other stars. Observations of exoplanets reveal a wide diversity of orbital configurations, many shaped by gravitational interactions similar to those in our own system. Hot Jupiters, eccentric super-Earths, and multi-planet resonances illustrate how gravity can produce both stability and dramatic rearrangement. By comparing these systems to our solar system, astronomers gain insight into universal processes, showing that the same force that anchors Earth and its neighbors also sculpts planetary systems across the Milky Way. Ultimately, gravity can be seen as the invisible architect of the solar system, shaping its structure, guiding its evolution, and maintaining its delicate balance. From the sun's overwhelming pull that governs planetary orbits to the subtle nudges that trigger cometary journeys from the Oort cloud, gravity organizes matter across vast distances and immense timescales. It preserves stability while enabling change, protects inner planets while sculpting outer-large realms, and drives both the grand architecture and fine details of celestial bodies. Without gravity, the solar system would be a chaotic scattering of matter rather than a coherent, evolving system. Gravity's influence is as profound as it is subtle. It shapes the very conditions that allow planets to form, moons to orbit, and life to exist. It connects the smallest asteroid to the largest gas giant, the sun to the farthest comet, and the solar system to the galaxy itself. It is a force that binds, protects, and orchestrates, producing the harmony and dynamism observed in the heavens. Understanding gravity, therefore, is key to understanding the solar system, offering insights into the past, present, and future of our cosmic neighborhood. In conclusion, the solar system is a testament to the power of gravity. Every planet, moon, asteroid, and comet moves according to its subtle but persistent pull. Gravity governs collisions and formations, stabilizes orbits and rotations, and preserves the order that has allowed life to flourish on Earth. It acts as both creator and preserver, balancing chaos and order, shaping structures from the largest planets to the smallest particles. As we explore the solar system and study distant exoplanets, we continue to uncover the pervasive influence of this universal force. Gravity is not only the foundation of celestial mechanics, but the architect of cosmic evolution, ensuring that the solar system remains a coherent, dynamic, and awe-inspiring system for billions of years to come. The story of gravity and the solar system is ongoing. As we peer deeper into space and refine our understanding of physics, new discoveries reveal additional layers of complexity, interactions, and consequences. Gravity will continue to shape the solar system, influencing planetary migrations, collisions, and the fates of distant icy bodies. It will continue to challenge and guide explorers, inspire scientists, and maintain the intricate cosmic ballet that defines our solar neighborhood. In every orbit traced, every tail of a comet illuminated, and every tidal wave upon a planetary surface, gravity's unseen hand is at work, reminding us that the universe is a structured, dynamic, and ever-evolving masterpiece orchestrated by one invisible yet omnipresent force.